my children. Hope you are all doing well. In the last video, we learnt about filling of orbitals with electrons. So now we are going to learn about electronic configuration followed by exchange energy. This can be done based on half-fast principle, then Pauli's exclusion principle, then third one is Hans rule. Okay. So we have learnt about these three with the suitable examples in the last video. So this will help you to do this electronic configuration well now. The basic formula to be followed when you write the electronic configuration is N, L, the power X. Here N denotes your principal quantum number and your L denotes azimuthal quantum number, that means your orbitals. X denotes number of electrons. Now let us write the electronic configuration of one or two elements. First you can write for hydrogen, you know very well, put orbital 1 is, you have only one electron. This is for hydrogen. Then you can write for helium, when you take helium atom, you have got 2 electrons. So this electron takes clockwise rotation, this will take anti-clockwise rotation due to spin of the electrons. Okay, so spin quantum numbers are different, that's why we denote like this way. Now let us go to the next element, nitrogen. Now when you take nitrogen, you have 7 electron, atomic number is 7. When you write the electronic configuration, first you write the orbitals in the increasing order of energy level according to half-fast principle. So 1 is, here it is, 2 is, after 2 is, write 2p. Now when you write the configuration, you will write 1 is 2, 2 is 2, 3, 2p3 will put. They are not degenerate orbitals, single orbitals. Now when you come to degenerate orbitals, am I right? No, this is wrong because Hans rule says no pairing should occur until all the available orbital gets at least one electron. So after putting this electron, next you must go to the next orbital, y orbital, place the next electron. Then third electron. No pairing these electrons. All the three are having same spin. Okay. So this is the electronic configuration. This is called electronic configuration. This is called orbital structure. Chlorine, atomic number is 17. We can write the configuration as we learned in the increasing order of energy levels. Follow this formula NLX. So 1 is 2, 2 is 2, 2p6, 3 is 2, then 3p5. Okay. So here and all you will put 1 is 2 over this 2 is 2. Okay. Then 2p6. 1, 1, 1. Okay. Then only we start pairing. Beautiful. Next you are going to 3s orbital. Your 2 electrons. So how many electrons you have filled? 2, 4, 6, 8, 10, 12 over. Okay, now you have got 5 more electrons because atomic number of chlorine is 17. 17 electrons are there. Okay, now we are going to the 3p orbital. Here you have got, but it is 3px, 3py, 3pz. First you have to give one electron, then only you must start pairing. So now we have learned how to write the electronic configuration. At the same time, you should know what will be the stable electronic configuration. So stability of orbitals. Only half filled and completely filled or half filled, fully filled orbitals will be stable. So that can be explained by taking two examples, chromium and copper. Chromium atomic number is 24. So when you write the configuration, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. This is called the expected configuration. Now actual configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Here, one electron from s orbital will jump into the d orbital. That is called excited state, which I mentioned in the previous video. Okay, this is your lower energy level, this is your higher energy level. So this electron, the second electron is moving to the higher energy level 3d orbital. So your configuration will become 4s1, 3d5. Now this is the actual configuration, which is the stable configuration. Same way you can take copper. Here the number of electrons are 29. Atomic number is 29. How can we write the configuration for this? So expected configuration is, expected one is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. So this is the expected configuration. Now this is actual configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6. Here what will happen? One of this s electron will jump up to this d orbital. So you will get 4s1, 3d10. Hope you all understood. Now this is the stable configuration. Okay, so now what we can conclude, when the orbitals gets either half filled or completely filled, which is called fully filled, both the configurations are stable configurations. So we can say the orbitals half filled, fully filled, these two are stable. So what are they? If it is s orbital, here fully filled is 2. P orbital, here it is 3, here it is 6. D orbitals mean 5, here it will be 10. F means here it is 7 and here it is 14. Both half filled and fully filled configurations are stable configurations. Have you all understood? Now we are going to see the stability is due to what? That is due to two reasons. One is due to the symmetric distribution of what? Electrons. Second reason is due to higher exchange energy. Let me take this 3d orbital for chromium. So in the expected configuration, your d orbital gets only 4 electrons. This is called partial configuration. Okay. This is not symmetric distribution. One is empty. But symmetric distribution means in. So this is called symmetric distribution of electrons. Now when you see the stability, we learned that is due to two things. One is symmetrical distribution, another one is exchange energy. That symmetrical distribution, what we learnt is half filled and fully filled configurations will give symmetrical distribution. Symmetrical distribution will give more stability. Why so? That is because here we have same spin of electrons. Spin of the electrons will be same in the half filled as well as in the fully filled. Here the shielding effect of one electron on other one of this electron will not shield this electron towards the nucleus. So shielding effect will be very, very small. Shield so that yes, nuclear attraction will be more. So that only symmetrical distribution is increasing the stability. So when you have inner electron, this is your inner orbital, this is your outer orbital. Now this inner electron will put a shield. Okay, this will be a screen for this electron so that this electron cannot attract the nucleus so forcefully. So this effect is called screening effect. If the screening effect is greater, the attraction will be lesser. When there is greater nuclear attraction, stability of the molecule will be, stability of the atom will be more. Okay, that's why we say symmetrical distribution will increase the stability. What about the next one? Exchange energy. Okay, for the same case, when you have two or more electrons in the degenerate orbital with the same spin, they can exchange their position. Are you clear? When you have two or more electrons with the same spin in the degenerate orbitals, they can exchange their position. This electron can go to this orbital or it can go to this orbital, not at the back. Okay, and the same way this electron can go to this orbital. So during this exchange, they will release energy. That releasing of energy, the amount of energy released is called exchange energy. So greater the exchange energy, greater will be the stability. So let us calculate and see what is exchange energy for fully filled or half filled configuration. I have taught you how to write the configuration of chromium. In chromium, the outermost configuration. Let us calculate what will be the exchange energy for these electrons. The first one, D4, which is called expected configuration, is otherwise called partially filled. Here this is half filled configuration. So now let us calculate. So when you take D4, now the first electron is going to change its position over here. Okay, 1, and it can go here also 2 and 3. So here the exchange energy is 3. When you take the next electron, second electron, 4. Now the second electron is exchanging here. Okay, so 2. Then for the, now this electron is going to exchange over here. So you will get 1. So total exchange energy is equal to 3 plus 2 plus 1, which is equal to 6. So for 3d4 orbital, your exchange energy is 6. Now let us take for 3d5. 1, 2, 3, 4, 5. 5 electrons in the d orbital in the case of chromium, which is the actual configuration, stable configuration. Now we are going to see why we say it is a stable configuration, because its exchange energy is greater. Now when you take 3d5, for the first electron, first position, it can change here 2, 3, 4. So 4 is the exchange energy. So when you take the second electron, it can go up to here 2, 3. So here it is 3. Now we are going to take the third electron. So 2 exchanges are possible. So here it is 2. Now for the last electron, 1 is possible. So what is the total exchange energy for d5 orbital is equal to, first one is 4 plus 3 plus 2 plus 1. So which is equal to 10. So now you compare these two. D4 orbital has got exchange energy 6. D5 orbital has got exchange energy 10. Okay, so which is greater? 10. Greater the exchange energy is greater means stability also will be greater. This is the basic for Hund's rule also. Have you all understood? Okay, so by this we are finishing this lesson. Unit 2. Hope you all very clear about energies of the orbitals as well as the stability of orbitals. Thank you so much.